Hey folks, Mr. Reed here. Welcome to the first and possibly last, depending on how long it takes, installment of video notes. Today we're going to be talking about complex numbers, which if you can't see are cool. It still can't really read that, that's okay. Anyways, if you are following along in the book, this will go along with Chapter 2, Section 4. So let's get started. First off, a little warm-up, just a little practice, remind ourselves of where we came from. We want to find the equation of the parabola with that vertex that goes through that point right there. So we're going to need to use vertex form, aka standard form of a quadratic function, which looks like that. And remember that our vertex is the point h, comma k, and then we have our generic xy point. So let's just substitute those values into that equation. So negative 22 equals a. I don't know what a is, that's what I need to find, but I know that x is negative 1 minus h, which is negative 3. So minus negative 3 is the same as plus 3 squared, don't forget that squared, plus our k value, which is indeed negative. So I'm going to say minus 2. Now let's simplify. I'm going to add 2 to both sides to get negative 20 equals a times negative 1 plus 3 is, well, that's the same as 3 minus 1, so that's 2, and 2 squared is 4, so that's the same as a times 4. So to get a by itself, divide by 4 on both sides, and we get negative 5 is equal to a. You're not done yet, you almost are, but last step, just rewrite the equation. Y equals negative 5 times the quantity x, and it was plus, plus 3 squared, and it was minus 2. And check yourself, plug it into your calculator, check your vertex, make sure it's at negative 3, negative 2, and trace to the x value of negative 1, and make sure that it is corresponding with the y value of negative 22. Cool. Alright, so we got three main goals here. We want to talk about what complex numbers are, what the imaginary unit I actually is. We're going to do some addition, subtraction, multiplication, and division of complex numbers. And then we're going to do something really, really cool. We're going to completely factor an irreducible quadratic function, which means we have some quadratic function like x squared plus x plus 1, which you cannot factor using only real numbers. So I can't be like, what goes there, because you won't ever be able to do it. So we want to factor that using complex numbers. So before we do that, let's think about this. Why do we need complex numbers? Well, if this is my f of x equation, and notice I've set it equal to 0, which is the same as saying find the solutions to this equation. Well, if I solve it algebraically, I can subtract 18 from both sides, and I can divide by 2, and then I'm left with x minus 3 squared. And notice that we are taking the square root of a negative number, which up until this point we haven't been able to do. That's why we need the imaginary unit I. It allows us to take square roots of negative numbers. And it does it like this. I is defined as the square root of negative 1. And so let's then see what happens when we start talking about factors of I. And when I say factors of I don't actually mean factors of I at all. What I'm saying is let's raise I to some powers and see what happens. So if I is the square root of negative 1, then I squared is going to be the square root of negative 1 squared, which is going to be negative 1. Sweet. Alright, let's keep this going. Then I cubed, well, that's going to be the same as I times I squared, and we just said that I squared was negative 1, so this is going to be negative I. Cool, cool, negative I right there. And then finally, I to the fourth, we'll think of that as like I squared times I squared, which is negative 1, times negative 1, which is indeed 1. Sweet. So, no matter what power of I you have, you can always boil it down to one of these four simpler cases right there. So, for example, I to the 7th, if you think about it, this is a cyclic pattern. It's going to continue through, and a really nice way to figure out what large exponents of I are actually equivalent to is to think about the fact that, going back a page, we have 1, 2, 3, 4 different options. So if you take your exponent and divide it by the number of those options that we have, sorry, I meant to write 2 over 4 right there, and 3 over 4 right there, and 4 over 4 right there. Think about the decimal remainder that you're going to get. That's going to be 0.25, that's going to be 0.5, that's going to be 0.75, and that's actually going to be 1. So if we look at I to the 7th, if I take 7 and divide it by 4, you're going to get a decimal that is ending in 7.5, which tells me that it is the same as negative I. And think about it, we've got, we're doing this 7 times, we're raising it 7 power, so it's going to be I times I times I times I, so that's I to the 4th, which remember we said is the same as 1. So when we multiply another I in there, which is really our I to the 5th, it's acting just like I. So then I to the 6th and I to the 7th. I to the 7th is really the same as I cubed. And I cubed, if you jump back, is the same as negative I, because it's like I times I squared, and I squared is negative 1. So I to the 7th is actually equivalent to negative I. Crazy. One more example. I to the 38th, do the same thing. Take 38 and divide it by 4. And I don't actually need to really do that. You can just think about it logically. I know that 4 times 10 is going to give me 30. Whoa, that's not how math works. I know that 4 times 10 is going to give me 40. 40 being 2 integers away from 38. So that tells me rather than getting a 1 for my answer if it divided evenly, I know that my remainder is going to have to be 0.5 because I'm 2 out of 4 away from that whole number. So 0.5 is going to be the same as I squared, which is just negative 1. Sweet! Okay, so the whole point of talking about the imaginary unit I is because we get to do cool things with the imaginary unit I, sorry I had to burp, in the form of complex numbers, which follow that structure, a plus bi, where a and b are both real numbers. So for example, 3 plus 2i is a complex number, negative 7 minus 2.8i is a complex number, etc., etc., etc. So luckily, everything you could want to do with a complex number in terms of addition, multiplication is the word, and subtraction actually behave the way you would expect them to. So there's no weird trickiness that you have to deal with. You can just think of it as if you're combining like terms, where you have the real part, which you combine, like in this case the 1 plus 2, and then you have the imaginary part that you can combine, in this case 3 minus 1. Well, I meant to write, sorry, undo that. I meant to write 3 minus 1 because of that 1i right there. So just combine the real part and the imaginary parts. So we're going to get 3 plus 3 minus 1 is 2i, right? That's how you would expect it to work. Same thing with subtraction, except think of that as a negative 1 times that quantity right there, so you have to distribute it. So we're going to get 3 plus 2i minus 1 minus 4i. And then combine the like parts, the real part and the imaginary part. 3 minus 1 is 2, and 2 minus 4 is negative 2. So I get 2 minus 2i. Cool, cool, cool. Multiplication, again, think of it like you're distributing, and so you have to FOIL to all your terms. So 2 times 1 is 2. Whoa, 2 times 1 is 2. 2 times negative I is negative 2i. 3i times 1 is 3i. And 3i times negative I is negative 3i squared. Notice I took the real part, the real coefficients there to get my negative 3, and then I times I is I squared. Now let's simplify this real quick, but remember that I squared is the same as negative 1. So really right there we have negative 3 times negative 1. So remember that in a moment. So we have 2 minus 2i plus 3i is going to give me a positive 1i. And then I have minus 3 times negative 1 is really plus 3. So I've got 5 plus I. Cool, cool, cool. Everything's awesome so far, but it gets even more awesome, because check this out. When you multiply these two together, we're going to get 3 times 3 is 9. We're going to get 3 times negative 2i is negative 6i. We're going to get 2i times 3 is positive 6i. And we're going to get 2i times negative 2i is negative 4i squared, which is the same as positive 4. So let's simplify this. 9 plus 4 is 13. Negative 6i plus 6i is 0. Well, look at that. We just multiplied two complex numbers together, and our answer was real. That's pretty cool. These are not just any ordinary complex numbers. These two complex numbers are called complex conjugates of each other. And notice complex conjugates are of the form a plus bi. If that is one of your complex numbers, then the complex conjugate of that number is a minus bi. See how we have the plus 2i and the minus 2i? And the a and b pieces are exactly the same. You might have seen this before last year when you're doing some stuff in, say, the trig world, where you're trying to rationalize the denominators. It's the same idea. So, when you multiply two complex conjugates together, your answer is a real number, and it's going to be a squared plus b squared, which is pretty cool and super helpful. So let's use that to our benefit right here, because we want to rewrite this following thingy as a proper complex number. So I'm trying to get it into the form a plus b I, and right now it's set up as this ugly division problem. But never fear, just like you did in the trig world last year, we're going to multiply by the complex conjugate of this. And notice it's a complex conjugate of the denominator, because I want to get the imaginary part out of the denominator. I want to have a real denominator. So I can do that like this. I can multiply by the fraction 2 minus 4i over 2 minus 4i, because that is equal to 1. So I'm not really changing my function at all. So when you multiply two fractions, multiply across the numerator and multiply across the denominator. The numerator, I'm going to get 3 times 2 is 6. I'm going to get 3 times negative 4i is negative 12i. I'm going to get I times 2 is 2i, a positive 2i. And I'm going to get I times negative 4i is negative 4i squared, which is positive 4. Notice that I squared is always going to change that sign. And then in the denominator, it's going to be a squared, so 2 squared is 4, plus b squared, and b is 4, so it's going to be 4 squared is 16. Let's simplify this some more. Numerator, notice I've got a negative 12i and a positive 2i, so I'm going to end up with a negative 10i imaginary component, and a 6 and a 4 gives me a positive 10 real component, and 4 plus 16 is 20. So let's simplify this even more. 10 over 20 is 1/2, and negative 10 over 20 is minus 1/2 I. Sweet! That is much prettier than that, at least in my opinion. So let's now talk about some other cool things. So a super awesome property of complex numbers is as follows. If I have, say, some cubic function like that has one real solution, one x-intercept, well, I know that every polynomial of degree n can have at least n real solutions. Well, it's going to have exactly n solutions if you include complex solutions. So that's a really cool thing that I'm just breezing over right here. But since there's one real solution to that, I know there has to be two non-real solutions to this same thing. And what's awesome is that if you know one complex solution, you automatically get another one for free, because they will always occur in conjugate pairs. So that means if I tell you that 2 plus 4i is a solution of a polynomial function, then you also know that 2 minus 4i is a solution to a polynomial function. That's actually really cool. You might be thinking to yourself, well, Mr. Reed, that's stupid. I don't care. Why does that matter? And you just used that S word that you don't like to use. Why are you being a punk? I don't know. I just am sometimes. But think about this. If we wanted to write this as a factor, I know that I can write it as a linear factor, x minus that quantity, 2 minus 4i, for one of them. And since it's occurring as a complex pair, conjugate pair, I know I'm going to have x minus the quantity 2 plus 4i as well. And then I can simplify these factors to x minus 2 plus 4i times x minus 2 minus 4i. And that's actually really cool, because check this out. If I know that these are solutions, since I knew that those were solutions of my polynomial, I could write them as linear factors of my polynomial, and now I can do this. I can multiply them together. X times x is x squared. X times negative 2 is negative 2x. X times negative 4i is negative 4i x, and I'm just distributing, and now I'm foiling, but there are 3 terms in each, but that's okay. Negative 2 times x is negative 2x. Negative 2 times negative 2 is positive 4. Negative 2 times negative 2i is positive 8i. Now in my last term, 4i times x is positive 4ix. 4i times negative 2 is a negative 8i. And where am I? 4i times negative 4i is a negative 16i squared, which is the same as a positive 16. So let's go through and simplify some things. First off, I've got my x squared. I've got a negative 2x and a negative 2x there, which will combine to give me a negative 4x. And I have a negative 4ix there, canceling with a positive 4ix there. I have a positive 8i there, canceling with a negative 8i there. My dog's trying to break into the room. I'll get her in a second. And then finally, I have a positive 4 and a positive 16. So those ugly, ugly linear factors, complex linear factors, give us this beautiful quadratic equation, x squared minus 4x plus 20. So if I had an original equation and I was told, say, this was like a cubic function, I could then divide that cubic function by this and find the real solution. That is awesome. Whoa, 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 real quick. So negative 49, square root of negative 49, well, that's the same as I times square root of 49, which that's a property, right? Because negative 1 times 49, square root of that, right? I can simplify it in there. And then I could rewrite that as negative 1 times square root of 49, and square root of the negative 1 is that I right there. So that's what I was just doing. But then you can simplify the real part to get 7i. So do that. Simplification. Simplify things. It's good. Okay, cool. But why? Why are we doing this, Mr. Reed? Who cares? I don't. Do you? Yes, I do, actually. It's sweet. It's fun. Because what I was alluding to a moment ago, if you incorporate complex numbers, it will allow you to completely factor any polynomial in a distinct number of linear factors. So that means if we have a quartic function, x to the 4th plus 3x cubed minus 27x plus 28, we could factor that as x minus blah times x minus times x minus times x minus blah, with our a coefficient out front. And maybe all of those factors are real and you get 4 real solutions, or maybe 2 of them are real and 2 of them are imaginary, or maybe all of them are imaginary and there are no real solutions. But either way, we can do it, and that's pretty cool, because you used to think that you couldn't do that with some quadratics, but now you know you can. So let's actually do that now. So we want to find the solutions to this quadratic function, and then we're going to see what we can do with it. So I'm going to substitute values in, so x equals negative b. Well, b is negative 4, so negative 4 is positive 4, plus or minus the square root b squared, negative 4 quantity squared is positive 16, minus 4 times a, which is 1, times c, which is 13, all of that over 2 times a, but again, a is 1. Let's keep going for plus or minus square root of 16 minus some number. Let's figure out what that number is. Well, 4 times 13, I don't immediately know what that is. Maybe you do. Maybe you're better at mental math than me. But I do know that 2 times 13 is going to be 26. So then I can just multiply 26 by 2. 26 times 2 is 52, I think, unless I'm just like messing something up. So 16 minus 52, we need to figure out what that is, and then blah, 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 blah. So 16 minus 52, well, I'm just going to do 52 minus 16 because that's easier for my mind. 52 minus 2 is 50. 50 minus 4 is 46. 46 minus 10 is 36. So we've got 4 plus or minus the square root of 36, which is 6. And, oh, I'm messing up my mind, my bad. Let's do that mental jaunt real quick. I did 52 minus 16, but the problem says 16 minus 52. 52 minus 16 is the opposite of 16 minus 52. So when I got 36, really, I'm dealing with negative 36. Otherwise, this problem doesn't really make sense in all this context. So that's going to be 4 plus or minus. Instead of 6, I'm going to have 6i all over 2. And I can simplify that to 2 plus or minus 3i, and that is it. So the two solutions are going to happen at 2, comma, wait, whoa, what am I doing here? Come on, Mr. Reed. 2 plus 3i and 2 minus 3i. Sweet. And let's do this because it's going to be awesome. So again, remember what I was saying about linear factors? That's going to tell me that, whoa, what's going on here? That's going to tell me that I can factor this as x minus 2 plus 3i times x minus 2 minus 3i in parentheses there. So let's see what happens when we do this. Let's simplify it some more first. X minus 2 plus x minus 2 minus 3i. I was thinking about something else there, sorry. X minus 2 plus 3i, because the negative and the negative. Okay, now let's distribute this in. I know I'm going to get an x squared term. I know from the negative 2 times the negative 2, no, whatever, we'll just do it for this time, but we'll do it mentally later. So x squared, x times negative 2 is a negative 2x, x times 3i is a 3ix, negative 2 times x is negative 2x, negative 2 times negative 2 is positive 4, negative 2 times 3i is minus 6i, then the last one, negative 3i times x is negative 3ix, negative 3i times negative 2 is positive 6i, and finally, negative 3i times 3i is negative 9i squared, which is positive 9. And let's simplify this. X squared minus 2x gives me minus 4x. Positive 3ix and a negative 3ix cancel out. Negative 6i and a positive 6i cancel out. And I'm left with 4 plus 9, which is 13. Which is what we started with. Come on, that's super cool. You have to pretend at least that that's cool. For me, please, just do it. And all I just did was what I was supposed to do on this page, but I did there. So let's move on to the last problem that you are looking at. It's no different than what we just did. We're going to do the same exact thing pretty much. So 2 minus I is a solution to that polynomial, so that tells me that I know there's a linear factor, x minus 2 plus I. Notice that I just distributed because I was doing negative 2 minus I gives me a negative 2 plus I. I know that that is going to be a factor, but I also know that the complex conjugate is going to be a solution, which means I have the factor x minus 2 minus I as well. And now I can multiply these together and see what I get. And I will get a quadratic function which is cool. So I'm going to do this one mentally. I'm going to get x squared from the x times the x. Let's think about my x terms. I'm going to get a negative 4x because of those negative 2's and those x's right there. And then think about the real constant component. I'm going to get that negative 2 times negative 2, which is going to give me a positive 4. But I'm also going to get an I times a negative I, which is negative I squared, which is positive 1. So I'm going to get negative 2 times negative 2 is positive 4, plus 1 is 5. You will get better and better at this, and you'll be able to do stuff like that too. I know it's so impressive. Mr. Reed does it all the time when he goes out and he wants to make new friends. So, what now? I want to find all real and imaginary solutions of this polynomial and factor it completely. Well, in order to do that, I need to use long division because I just found what my two linear factors multiplied together equals. I get a quadratic function. If I take that quadratic function out of f of x, i.e. divide by that quadratic function, I will know what is left. So let's do that. X squared minus 4x plus 5 is going into 2x cubed minus 14x squared plus 34x minus 30. Sweet, 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 sweet. So ask yourself, how many times does x squared go into x cubed? Well, it's going to need one factor of x to get from x squared to x cubed, and it's going to need a 2. So that tells me that I'm going to multiply it by 2x. And 2x times x squared is 2x cubed. 2x times negative 4x is negative 8x cubed. 2x times 5 is 10x. And now I need to subtract that entire expression there. So I'm going to change the sign of each of those terms. 2x cubed minus 2x cubed is 0. Negative 14x squared plus 8x squared is negative 6x squared. And 34 minus 10 is 24x, a positive 24x. Let's drop that negative 30 down now. How many times does x squared go into negative 6x squared? Well, negative 6 times. And I'm going to get negative 6x squared when I do negative 6 times x squared. When I do negative 6 times negative 4x, I'm going to get a positive 24x. And a negative 6 times a 30 is a negative 30. Notice that the last two lines of expressions are exactly the same. So when I flip all those signs to subtract the bottom away, I am going to get my remainder of 0. Cool! What does that tell me? Well, that tells me that 2x minus 6 is also a factor of this polynomial, which I can then factor a 2 out of to get 2 times x minus 3. And now, if I want to factor this completely, I need to think about my non-real linear factors, x minus 2 plus I, and x minus 2 minus I. Sweet, that is completely factored. That equals f of x. I promise you, that's super cool. And we can then go through and take all of our solutions. X equals 3 is going to be a solution. 2 minus I is going to be a solution. And 2 plus I is going to be a solution. So I'm done.